Hello guys, welcome back to my YouTube channel. Today I will be talking about carbon nucleophiles. And the most classic example of how a carbon nucleophile can be formed is by deprotonation. For example, we can take an alkyne and we can hit it with some base. And step one to every single reaction is always identifying who is nucleophilic and who is electrophilic, where the nucleophilic things are the things with the electrons. This will always be the driving force of organic chemistry and where your arrow pushing will start. Here we can see we have an NaNH2, so whenever we have a potassium, sodium, we kind of forget it's there and we're like, okay, whatever you're with is negative. It has electron density that can be used and it is nucleophilic. So this NH2 can take one of its lone pairs and go and attack something electrophilic on our starting material. But here, our starting material doesn't have any obvious electropositive carbons. For example, there's no halogen, like there's no bromine, where we can say that's delta minus, this carbon is delta plus, so it's our electrophile. No, we don't have that here. But what we do have is a triple bond. And at the end of this triple bond, we have a terminal hydrogen. And terminal hydrogens are actually quite acidic. They want to be removed. When you want to be removed, you're delta plus. You can be attacked by a base. So this NH2 can go to N. I'll draw this arrow in a different color because every arrow we draw from a lone pair will become a new bond. H, and then the two electrons in this CH bond will go up and on to this carbon at the end of the triple bond. So our product will look like this. We will have a negative charge on that terminal carbon. I guess now the question is, well, why was this hydrogen acidic? I can't really understand why it's acidic. We always want to argue acidity of a proton based on the stability of the conjugate base. This would be the conjugate base. This negative charge is actually quite stable. When looking at stability of the conjugate base, we can argue based on REO. So A stands for atom, R stands for resonance, I stands for inductive effects, and O stands for orbital. Here, we're going to argue stability of the conjugate base based on the orbital. This is an sp hybrid orbital. It is 50% s, 50% p. To really dial in this concept, let's look at the hybridization of this carbon. This would have 3 hydrogens. It would be an sp3 orbital. What would be the percentage of s? So this would be 25% s, 75% p. Hope that makes sense. So now if you increase the percentage of s, you are technically increasing. A way to think about this is the amount of nucleus likeness. So hence the nucleus is positively charged. And negative charges, since opposites attract, like positive charged things, so the more percent s you have, the more stable this negative anion will be. So we can make a little trend. So we have sp, we have sp2, we have sp3. So increasing this way, we have increasing stability of a negative charge. So this will be our intermediate form. So we can take this compound and react it with the next reagent. For the next reagent is an alkyl group with an iodine. So we have 3 carbons and an iodine group. So get into a habit of always labeling all your lone pairs. So this iodine will have 3 sets of lone pairs, 6 electrons. It is delta minus, it is a halogen, hence it will be sucking electrons away from this carbon and there will be a dipole moment. This carbon will be electrophilic, and since opposites attract, this carbon, previously deprotonated, will be a nucleophile and it will attack this delta plus carbon via 2 in, 2 out. Always label your carbons so you do not add or drop carbons. So 1, 2, 3, 4, 5. And this labeling is very arbitrary. 6, 7, 8. Just so you do not add or drop any carbons. So draw in your bonds that you previously had. Atom 1, 2, 3, 4, 5. And then the arrow you drew, so here this pink arrow from the negative charge becomes a new bond. So new bond to atom, we labeled it 8. And then atom 8 is connected to 7, and 7 is connected to 6. 7 is connected to 6. And this is your product. And then you have a plus I, and it initially had those 3 sets of lone pairs. And it would also gain that extra lone pair that was initially in the Ci bond. But we still have the Na plus, which will be used for charge balancing. That's it. That's all for this question. Hope this makes sense. So we can move on to question number 2. All right, so for question number 2, step 1, you always want to identify who is electrophilic, who is nucleophilic. So here we have a delta minus bromine and a delta positive carbon. So this carbon will be electrophilic, as it is in a deficit of electrons, so nucleophilic things will be attracted to it and attack it. Where's our nucleophile? Well, here we have the same thing where we have this NH2 group that will attack the H2 in, 2 out. What do you get? So you get a nucleophile minus charge. So this nucleophile, which is nucleus loving, remember, so it likes positively charged things, will attack the delta plus carbon connected to the bromine on the starting material. So 2 in, 2 out. I'll label this bond in green, 2 in, 2 out. The ring did not change. We did not add or drop or change anything a part of the ring, and it was connected to 1 carbon. And that carbon was attacked, so a new bond was made via that green arrow, which was connected to a triple bond. And that triple bond had 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons. 3, 4. Bada bing, bada boom. This is your product. And then plus a Br minus, where it initially would have had 3 sets of lone pairs. 1, 2, 3. But then it would have gained the 2 white electrons that initially were in the C-Br bond, and hence it will be negative, but we still have that Na plus for charge balancing. That is it. That is all. Hope that makes sense. Let me know if you have any questions. Make sure to leave a like, comment, save, and or subscribe to my channel, and leave a comment below telling me what concept you'd love for me to cover next. Have a great day.